Almost none of your weight is matter. Step on a scale tomorrow morning, and whatever number comes up, about 99% of it is not the mass of anything you are made of. It is energy, motion, and binding, and a quantum effect that has no name in ordinary language, held in place inside particles that have no surface anywhere. The particle is the proton. There are around 10 to the 28th of them inside you, and it is the most studied object in the history of physics. After a century of work, nobody can tell you how big it is without first asking which definition of size you meant. Nobody can list what is inside it. Nobody can account for the direction it points. And underneath all of that sits a fifth question, older and heavier than the rest. Every other particle of its kind falls apart. This one has never once been seen to. Nobody knows whether that means it cannot. Get comfortable. Hit subscribe if this is your first time here, because by the end of tonight you will know exactly why the proton refuses to die, and why both of the possible answers are worse than the question itself. Now, let's slowly ease into this. Part 1. The most familiar object in the universe. There is an object inside you right now that physics has been studying for more than 100 years, and after all that time, nobody can tell you how big it is. Not approximately, not within a reasonable margin. The number that appeared in every textbook on Earth for decades turned out to be wrong, and the correction arrived without an explanation attached. That is only the first of the problems, and it is not the worst one. The object is the proton. You are not going to be surprised by the name. You met it in a classroom at some point, probably drawn as a small shaded circle at the center of an atom, sitting comfortably beside its neighbors, labeled and finished and understood. It was one of the easy ones. Electrons were strange, quantum mechanics was strange, but the proton was the solid part, the piece of the picture that behaved. It was the thing everything else was arranged around. Consider how much of you it accounts for. A human body of ordinary adult size contains something on the order of 10 to the 28th protons. That is a 1 followed by 28 zeros. If you tried to count them at a rate of 1 per second, starting at the beginning of the universe and continuing without pause until tonight, you would not have counted a billionth of them. They are in your bones and your blood and the water you drank an hour ago. Every atom of every molecule of every cell you are built from is arranged around a small cluster of them, and almost all of your weight comes from what those clusters are doing. Step back from your body, and it does not get less common. Hydrogen makes up roughly 3/4 of the ordinary matter in the universe by mass, and a hydrogen nucleus is one bare proton and nothing else. Every star you have ever seen is a sphere of them, crushed together and fusing. The gas drifting between the stars is mostly them. When astronomers talk about the ordinary matter in the cosmos, the matter that is not dark, the matter that emits light and forms planets, and eventually forms people, they are talking about a universe in which the proton is the overwhelming default. It is not a special case, it is the standard unit of stuff. It is also very small in a way that is difficult to make real. An atom is already beyond ordinary imagination, but the nucleus at its center is smaller than the atom by a factor of about 100,000. If you scaled an atom up until it was the size of a large sports stadium, the protons at the center would be a grain of rice on the center spot, and everything else in that entire volume would be the faint statistical presence of electrons. The solidity of the floor under you, the resistance of the table when you put your hand on it, comes almost entirely from empty space refusing to be occupied. The matter itself is a rounding error. It is also, without much competition, the most examined particle in the history of experimental science. Physicists have fired electrons at it, fired muons at it, fired other protons at it, at nearly the speed of light. They have built machines the size of towns to take it apart, They have watched enormous volumes of it in the dark for decades at a time, waiting to see one of them break. There is no object in nature that has received more sustained, expensive, careful attention. If there is anything in the universe we ought to have finished by now, it is this. You know what you were told about it. A proton is made of 3 quarks, 2 of one kind and 1 of another, held together by the strong force. 2 up quarks and 1 down quark. That sentence is in every introduction to particle physics ever written, and it is not exactly false. It gets the electric charge right. It gets the behavior right in the specific narrow sense that the arithmetic of charge works out. It is a useful thing to say, in the way that saying a country is made of its provinces is a useful thing to say. Here is what that sentence leaves out. Those 3 quarks account for less than 1% of the mass of the proton. They account for about 1/3 of its spin. They do not tell you where its outer surface is, because it does not have one. And if you go looking inside a proton with enough energy, you do not find 3 of anything. You find a shifting, boiling population of particles, whose number depends on how hard you look, including, in a result published only a few years ago, a particle that weighs more than the proton that contains it. That is the shape of tonight. Not one mystery, which would be ordinary, because physics has plenty of those and lives comfortably with them. 4 separate failures, stacked on top of each other, all attached to the same small object, all of them getting stranger the more precisely we measure. Nobody can state the proton's size without first specifying which of several incompatible definitions of size they intend. Nobody can say what is inside it in the sense of giving you a list. Nobody can derive its mass in a way that a human being can hold in their head, even though a computer can calculate it correctly. And nobody, after nearly 40 years of trying, can account for the direction it points. Then there is the 5th question, which is the one we will not answer until the very end, and which is the reason any of the rest of it matters to you personally. Every other particle of its kind falls apart. A neutron on its own lasts about 15 minutes before it decays into something else. Every heavy particle ever catalogued in a collider has a lifetime, usually a brutally short one. The proton appears to be the sole exception. It appears to simply persist, indefinitely, for as long as you care to wait. Nobody knows whether that is true. That is not a poetic way of saying, it is probably true, and we are being cautious. It is the literal state of the evidence. There are people who have spent their entire working lives on the question, in a room under a mountain, and what they have to show for it is a lower limit and a silence. By the end of tonight you will know exactly why the proton refuses to die, why both possible answers are unwelcome, and why the second one is arguably worse than the first. Notice what has already happened here, because it is the thread that runs through everything that follows. Our ability to measure the proton has improved by something like a factor of 1,000 over the last century. Our ability to explain it has not moved anything like as far. Those 2 curves were supposed to travel together. The entire promise of precision, the reason anyone builds a better instrument, is that a sharper picture resolves into a clearer understanding. With the proton, that has not been what happened. Each increase in precision has revealed a new way in which the previous description was a convenience rather than a truth. There is a temptation, when a story like this is told, to arrive at the reassuring conclusion that science is self-correcting and everything will be tidied up in due course. Some of it probably will. A machine is being built right now, at a cost of billions, for no other purpose than to answer 2 of the questions we are going to walk through. But the reason that machine is being built is that these questions are open, and they have been open for a long time, and the people who understand them best are not confident about how they will turn out. So set aside the shaded circle from the classroom diagram. The most familiar object in the universe is not a small ball of positive charge sitting quietly at the center of an atom. It is something considerably harder to describe than that, and the century of work that was supposed to pin it down has mostly succeeded in showing how much of the original description was scaffolding. To see how we arrived here, we have to go back to the moment the proton was invented. Not discovered exactly. Invented, in the sense that somebody had to decide that a particular thing was a thing at all, and give it a name, and persuade everyone else that it belonged in the picture. That happened in a laboratory in the north of England, and the man who did it was not looking for a proton. He was looking at what happens when you fire something very small at something very thin, and get an answer nobody expected. Part 2. How the proton was invented. The story begins in Manchester, in 1911, with an experiment that Ernest Rutherford did not perform himself. He designed it, and he interpreted it, but the long hours in the dark belonged to Hans Geiger, his assistant, and to a 20-year-old undergraduate named Ernest Marsden. The setup was simple enough to describe in a sentence. Take a source of alpha particles, which are small, fast, positively charged fragments thrown out by radioactive material. Aim them at a sheet of gold, hammered so thin it is only a few hundred atoms deep. Then sit in a darkened room for hours and watch a screen for tiny flashes of light where the particles land. It is worth pausing on what watching that screen actually involved, because it is easy to say and hard to do. There were no electronic detectors. A flash was a flash, seen by a human eye, and the eye had to be prepared for it. An observer would sit in a completely dark room for half an hour before starting, letting their vision adjust until they could register a single faint spark on a screen of zinc sulfide. Then they would count, out loud or with a tapper, while somebody else recorded the number. Concentration failed after about a minute, so the observers swapped in rotation, over and over, for hours at a stretch. Geiger and Marsden did this for months. The foundation of modern atomic physics was laid by two men taking turns in the dark, counting specks of light they could barely see. The expectation was that almost nothing would happen. The model of the atom in fashion at the time imagined positive charge spread evenly through the whole volume, with electrons distributed inside it, rather like fruit suspended in a pudding. A fast alpha particle passing through that would be nudged very slightly off course, and would carry on. It would be like firing a bullet through fog. The experiment was, in truth, a training exercise. Nobody expected a result. What Geiger and Marsden found was that a very small fraction of the alpha particles did not pass through. Roughly 1 in 8,000 came back. Not deflected slightly, not bent by a degree or two, but reversed, returned at a sharp angle towards the source. Rutherford spent a long time refusing to believe it, and when he finally accepted it, he described the feeling in a line that has outlived almost everything else he said. It was, he wrote, about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it had come back and hit you. The only way to get that result was to concentrate the positive charge. If the charge of an atom were spread thinly across its whole volume, nothing could push back hard enough to reverse an alpha particle. If instead it were packed into a tiny, dense knot at the center, then the rare alpha particle that happened to come almost directly at that knot would meet an enormous repulsive force at very close range and be thrown straight back. That is what the numbers demanded. Rutherford calculated how small the knot had to be, and the answer was that the atom is essentially empty, with a nucleus at its heart, perhaps 100,000 times smaller than the atom around it. That single conclusion rearranged everything downstream of it. The solid, filled atom was gone. In its place was a structure that was almost entirely nothing, with all its mass and all its positive charge crushed into a speck at the middle. Everything you touch, everything that holds shape, is built from objects that are overwhelmingly empty. And it took a couple of thousand flashes of light on a zinc sulfide screen in a darkened Manchester room to establish it. The next step took most of the following decade. Between 1917 and 1919, working partly alone while the First World War drained his laboratory of staff, Rutherford began firing alpha particles into nitrogen gas rather than at metal foil. He found that hydrogen nuclei came out. This was the important part, and it is worth being precise about why. Hydrogen is the lightest element, and its nucleus is the simplest possible positively charged object. Finding hydrogen nuclei emerging from nitrogen meant that the nitrogen nucleus contained them, or could be made to yield them. The hydrogen nucleus was not merely one type of nucleus among many, it was a component of other nuclei. It was a building block. Rutherford gave it a name around 1920. He chose proton from a Greek word meaning first, and the choice was not accidental. There had been a competing suggestion, Proton, honoring an English chemist named William Prout, who had proposed something remarkably similar more than a century earlier. In 1815, Prout had noticed that the atomic weights of the elements looked suspiciously close to whole number multiples of the weight of hydrogen, and he suggested that every atom might simply be built out of hydrogen atoms packed together. Prout was ridiculed for it, and the ridicule was based on good evidence. As measurements of atomic weights improved through the 19th century, the whole number pattern broke down. Chlorine came out at about 35.5 times the weight of hydrogen, which is not a whole number of anything. The idea looked dead. It stayed dead for over 100 years, until the discovery of isotopes explained that the chlorine sitting in a chemist's sample is a mixture of two slightly different varieties, and that the awkward fraction is an average of two clean whole numbers. Prout had been right in spirit and wrong in detail, and by the time anyone could demonstrate that, he had been dead for over 50 years. Rutherford also, in the same period, proposed something he had no evidence for at all. He suggested that there ought to be a neutral partner to the proton, a particle of similar mass carrying no charge, because otherwise the arithmetic of nuclear masses did not work. He was right, and it took 12 more years and a former student of his, James Chadwick, to find the neutron in 1932. The picture that resulted is the one most people still carry: a nucleus of protons and neutrons, a cloud of electrons, and three fundamental building blocks from which the entire material world is assembled. Consider how satisfying that was. In roughly 30 years, physics had gone from an atom that was a vague pudding to an atom with a precise architecture and a small set of named parts. The proton in that picture is elementary. It is not made of anything. It is a point of positive charge with a certain mass, indivisible, one of the small handful of things that simply exist and out of which all other things are constructed. There is nothing further to ask about it. You could put it in a textbook and be done. There was one detail inside that satisfying picture which should have bothered people more than it did. The positive charge on the proton is exactly equal in size to the negative charge on the electron, to as many decimal places as anyone has ever been able to check. Experiments have compared them and found them identical to better than 1 part in 10 to the 21st. That is a strange thing for nature to arrange. The proton and the electron have nothing else in common. Their masses differ by a factor of more than 1800. They respond to different forces. They were, as far as anyone could tell, entirely unrelated objects that had simply been issued with charges of precisely matching size and opposite sign, and nobody could say why. If those two numbers differed by even a minuscule fraction, the electrical repulsion between the atoms in your body would overwhelm gravity, and matter, as we know it, could not hold together. The picture was tidy on the surface, and had an unexplained coincidence buried at the bottom of it. That turns out to be a pattern. Physics believed that, more or less, for 40 years. It is a period worth sitting with, because it is the last time anyone could give a complete and confident answer to the question of what a proton is. Every decade since has subtracted something from that answer. The subtraction did not begin with a grand theoretical revolution or a strange result from a collider. It began with a much more modest question, the kind of question a curious child might ask, and one that turned out to have no clean answer at all. Somebody wanted to know how big it was, not what it did, not what it weighed, not what it was made of, simply how far across it went, in the plainest sense of the question, the way you would ask about a stone or a coin. Part 3. Measuring something with no surface. The question sounds like the easiest one in the whole of physics. How big is a proton? You would think that after establishing it exists, giving it a name, and building an entire model of matter around it, somebody would have written the number down early and moved on. The difficulty is that the question quietly assumes something which is not true. When you ask how big an object is, you are assuming it has an outside. You are assuming there is a place where the object stops and the rest of the world begins, and that this place is the same regardless of who is asking or what they are using to look. A marble has that. A planet has that. Near enough. A proton does not. There is no shell, no skin, no boundary layer, nothing that a probe arriving from outside would register as an edge. What there is instead is a smear of electric charge, densest at the center and thinning outwards, fading away with distance and never quite reaching zero. So physicists did what you do when a quantity has no natural definition. They invented one. The number that gets quoted as the size of a proton is called the root mean square charge radius, and it is a statistical description of that smear. You can think of it as the typical distance of the proton's electric charge from its center, in the same way that you might describe the size of a crowd in a square by measuring how far the average person stands from the middle. It does not tell you where the crowd ends. It tells you how spread out it is. That distinction is going to become extremely important later, but for the moment it was a workable definition, and the job became measuring it. Two entirely different methods existed. The first is the direct one, and it is the descendant of what Rutherford did with the gold foil. Fire something at the proton and watch how it comes off. If the proton were a true point of charge, the pattern of deflections would follow a specific curve, worked out in the 19th century and named after Rutherford himself. If the charge is spread out over some volume instead, the pattern departs from that curve, and the size of the departure tells you how spread out the charge is. The probe of choice is the electron, because electrons feel electricity and are not affected by the strong force, so they read the charge distribution cleanly without getting tangled up in the internal machinery. The man who made this work was Robert Hofstadter at Stanford in the middle of the 1950s. Picture the room, a linear accelerator, a few hundred feet of it, pushing electrons up to energies that had never been available before, and at the far end, a magnetic spectrometer the size of a small house, mounted so it can be swung around the target to catch electrons that have scattered off at different angles. The target itself is unglamorous. It is hydrogen, cooled until it is liquid, sitting in a small vessel in the path of the beam. The beam runs. Electrons pour through the liquid hydrogen, most of them barely noticing it, a few of them striking close enough to a proton to be thrown sideways. The spectrometer swings to 20 degrees and counts. It swings to 40 and counts. It swings further, out to the wide angles where only the closest, hardest encounters end up, and the counting rate falls away, as everyone knows it will. The question is how fast it falls away. A point charge has an answer for that, and the answer is a smooth curve that has been on paper for 50 years. Night after night, the numbers come off the spectrometer and get plotted, and the plotted points do not sit on the curve. They sag below it, further and further below as the angle opens up, and the size of the sag is not noise and does not go away when the apparatus is checked. The proton is not a point. It has been giving off this signal since the beginning of the universe, and the room is quiet, and somebody is writing it down for the first time. Hofstadter's number came out at around 0.74 femtometers. A femtometer is 1/4 of a meter, a decimal point, followed by 14 zeros, and then a 1. The scale is genuinely hard to place beside anything familiar, but here is one attempt. A proton is to a grain of sand, roughly, as that grain of sand is to the distance from London to Sydney. Hofstadter shared the Nobel Prize in 1961 for the work, and the citation was for showing that the nucleon has structure, which is a polite way of saying he took the last simple thing in physics and demonstrated that it was complicated. The second method has nothing to do with firing anything at anything. It comes from spectroscopy, and it works by listening rather than by hitting. An atom of hydrogen has energy levels, and an electron moving between them absorbs or emits light at precise frequencies. Those frequencies can be measured with almost unreasonable accuracy, better than 1 part in a trillion in the best cases. Now here is the connection to size. An electron in certain orbitals does not orbit around the proton in the way a planet orbits a star. It has a probability of being found anywhere, including inside the proton itself. While it is in there, the electrical pull it feels is weaker than it would be from a point charge, because some of the proton's charge is now outside the electron rather than pulling it inward. That slightly changes the energy of that orbital, which slightly changes the frequency of the light. Measure the frequency precisely enough, and you can work backwards to the size of the proton. The effect being exploited here has its own history. It is a cousin of the Lamb shift, measured by Willis Lamb in 1947, a tiny discrepancy in the hydrogen spectrum that classical theory said should not exist at all. That measurement is often described as the experiment that launched modern quantum electrodynamics, because explaining it required physicists to take seriously the idea that empty space is full of activity, and that particles are constantly interacting with their own fields. It won Lamb the Nobel Prize in 1955. Hydrogen, the simplest atom there is, has repeatedly turned out to be the place where the deepest problems in physics show up first. Through the second half of the 20th century, both methods were refined. Scattering experiments got better beams, better detectors, better handling of the corrections. Spectroscopy got lasers, and then it got frequency combs, which made it possible to measure optical frequencies against an atomic clock and push the precision into a range that would have looked like fantasy in Hofstadter's day. And, crucially, the two methods agreed with each other. They were completely independent. They shared no apparatus, no technique, no assumptions to speak of. One of them hit the proton with a beam, and one of them read the color of light coming out of a gas. They converged on the same answer. The frequency comb deserves a moment of its own, because it is the reason the second method became so powerful. Before it existed, measuring the frequency of visible light directly was close to impossible, because light oscillates hundreds of trillions of times a second, and no electronics can follow that. The comb solved it by producing a laser output consisting of hundreds of thousands of evenly spaced frequencies, like the teeth of a ruler laid across the spectrum, with the spacing locked to a microwave signal that can be compared against an atomic clock. You no longer measure the light. You count which tooth it falls on. Theodore Hensch and John Hall shared the Nobel Prize in 2005 for it, and the effect on hydrogen spectroscopy was immediate. Transitions that had been known to a handful of digits became known to 14 or 15. This mattered for the proton, because the size of the proton is buried in those digits, a minute correction to a number dominated by other physics, and extracting it requires that everything else be nailed down first. By the 2000s, that answer had settled at approximately 0.8768 femtometers. It went into the CODATA tables, which are the internationally agreed reference values for the fundamental constants of nature, the numbers that every laboratory on Earth works from. It went into textbooks. It went into the calculations that other results depend on, including the value of the Rydberg constant, which is one of the most precisely determined quantities in all of science. Thousands of papers rested on it. That is what confidence looks like in physics. Not one measurement, but two unrelated measurements pointing at the same place, refined over half a century, adopted internationally, and built upon. If you had asked anyone in the field in 2008 how well we knew the size of a proton, you would have been told, correctly, that we knew it to a fraction of a percent, and that this was one of the more settled numbers in the discipline. Then a small team in Switzerland decided to try the same measurement with a different particle. Not because they doubted the answer, they expected to confirm it, more precisely than anyone ever had, and to be finished within a year or two. Part 4. The line in the wrong place. The Paul Scherrer Institute sits in the village of Villigen, in the north of Switzerland, on a bend of the river Aare. It runs one of the most intense beams of muons in the world. A muon is, for practical purposes, a heavy electron. It carries exactly the same electric charge. It responds to the same forces. As far as every measurement ever made can tell, it is identical to an electron in every respect except one. It weighs about 207 times more, and it falls apart after about 2.2 microseconds. Randolph Pohl and his colleagues had an idea that follows directly from that mass difference. If you build an atom of hydrogen but replace its electron with a muon, the muon, being so much heavier, orbits far closer to the proton, about 200 times closer, and because it is that much closer, it spends dramatically more of its existence overlapping the proton itself. The energy shift caused by the proton's size, the tiny correction that ordinary spectroscopy has to dig for, becomes enormous by comparison. The sensitivity improves by a factor of roughly 8 million. 8 million is not an incremental gain. It is the difference between straining to hear something and having it shouted at you. The plan was to measure the proton radius so precisely that the existing value would be confirmed to an extra decimal place, and the question would be closed for a generation. The engineering problem is the muon's lifespan. 2.2 microseconds is roughly the time it takes sound to cross a small room. Everything has to happen inside that window. The muon has to be produced, slowed, delivered into a chamber of hydrogen gas, captured by a proton, allowed to cascade down into the right orbital, hit with a laser pulse tuned to exactly the right frequency, and the resulting X-ray detected. If any stage runs long, the muon decays, and the event is lost. The apparatus took years to build, and the laser system had to fire on demand, within a fraction of a microsecond of a signal announcing that a muon had arrived. Consider also where the muons come from, because nothing about this is convenient. You cannot store muons. There is no bottle of them anywhere. They have to be manufactured continuously, and the way you manufacture them is to accelerate protons, slam them into a target of graphite or carbon, produce pions in the collision, and wait for those pions to decay, which they do, in a few tens of nanoseconds, into muons. The muons are then steered magnetically down a beamline into the experiment. Every muon that arrives in the hydrogen chamber has already existed for a meaningful fraction of its total lifespan, simply by traveling there. The experiment is therefore built around a particle that is being made a few meters away, arriving already partly spent, and dying while you work on it. The proton being measured, by contrast, has in all likelihood been sitting there since the first few minutes after the beginning of the universe. The measurement is a fleeting thing interrogating a permanent one, and the fleeting thing sets every deadline. Then there is the search itself. The team knew roughly what frequency to scan, because they knew the accepted proton radius, and from that they could calculate where the transition line ought to sit. They picked a range around that prediction, generous enough to allow for error, and they scanned it. They found nothing. Picture what that is like. It is the middle of the night in Villigen. The beam is running. The muons arrive, one at a time, a few thousand of them a second, and each one lives for 2 millionths of a second, and then is gone. The laser fires into the chamber at a set frequency, and the detectors watch for the X-ray that would announce a successful transition. The count sits at background. Somebody adjusts the frequency a fraction, and they run again, and it sits at background. Hour after hour, shift after shift, the number of things that could be wrong grows in everyone's mind. The laser timing, the gas pressure, the muon delivery, the detector calibration, the theory relating the frequency to the radius, the assumption that the atoms are even forming in the state everyone thinks they are. The obvious conclusion, the one any careful person reaches first, is that the mistake is theirs. It is always theirs. Experiments fail constantly, and physics is almost never wrong in a way that shows up in your own basement. So they check, and they rebuild, and they check again, and they come back and scan the same empty stretch of frequency, and it stays empty. They spent years like that. Then, in 2009, they widened the search. They scanned outside the window where the accepted proton radius said the line had to be, into a region that the textbook value ruled out. And there it was. Clear, strong, unmistakable, sitting well away from where a decade of physics said it belonged. The result was published in Nature in 2010. The proton charge radius from muonic hydrogen was 0.84184 femtometers. A refinement published in Science in 2013 brought it to 0.84087. The accepted value from electrons and spectroscopy was 0.8768. The gap is about 4%. Put in absolute terms, it is around 0.035 femtometers, which is a difference so small that it has no analogy in ordinary life at all. But size is not what matters here. What matters is precision. Both measurements came with error bars, and those error bars were small, and they did not overlap. Not slightly. The disagreement corresponded to roughly 5 standard deviations, and depending on which combination of datasets you used, some analyses put it as high as 7. In experimental physics, 5 standard deviations has a specific meaning. It is the conventional threshold for announcing a discovery. It is the bar the teams at CERN had to clear before they were willing to say they had found the Higgs boson. It means the probability of the result arising from statistical fluctuation alone is around 1 in 3.5 million. That threshold exists to protect the field from getting excited about noise. Here, the same threshold had been cleared by a contradiction. 2 well-established, independently developed methods for measuring the same property of the same object had produced answers that could not both be right, at a confidence level that would ordinarily be called a discovery. Except nothing had been discovered, something had been broken. Sit with what that meant for the people involved. A number that appeared in every physics textbook on the planet, that sat in the internationally agreed tables of fundamental constants, that thousands of published papers had used as an input, was under direct challenge from a result that would not go away, and the people who found it had spent months, then years, assuming that they themselves were the problem. That reflex is the most human thing in this entire story. A careful person, confronted with a result that contradicts the accumulated work of a century, does not conclude that the century is wrong. They conclude that they made a mistake somewhere, and they go looking for it. That instinct is correct almost every time. It is what keeps the field honest. And on the rare occasion when it is wrong, the only thing that gets you past it is stubbornness, the willingness to keep looking after you have run out of places to look, and then to scan the one stretch of frequency that the textbook says is impossible. The damage did not stay contained to one number either. The proton radius is tangled up with the Rydberg constant, which describes the spacing of the energy levels of hydrogen and is one of the most precisely measured quantities in the whole of science, known to about 12 significant figures. The two are extracted from the same spectroscopic data, and they trade off against each other. Shift your assumed proton radius, and the best fit value of the Rydberg constant moves to compensate. So a 4% disagreement about the size of a proton propagated directly into a wobble in a constant that physicists had regarded as one of the firmest numbers they possessed. For a while, there were serious papers asking whether the Rydberg constant itself needed revising. When one loose thread starts pulling on the tables of fundamental constants, the discomfort spreads quickly. The community's reaction was not immediate acceptance. It was, broadly, a search for the mistake. Perhaps the theory connecting the measured frequency to the radius was incomplete for muons. Perhaps some correction involving the proton's internal structure had been mishandled. Perhaps there was an unaccounted systematic in the older electron work. Hundreds of papers appeared over the following years. The problem acquired a name that stuck, the proton radius puzzle, and it became one of the most closely watched open questions in physics for the better part of a decade. And underneath the technical argument, there was a possibility that almost nobody wanted to say out loud too early, because saying it too early is how careers end. Perhaps neither measurement was wrong. Perhaps the muon and the electron genuinely see a different proton. If that were true, then one of the quiet structural assumptions holding up the entire standard model of particle physics would be false, and the consequences would run far beyond a number in a table. Two numbers, one object. Something had to give. Part 5. What a disagreement about a number means. When two measurements of the same thing disagree at 5 standard deviations, there are only 3 doors out of the room, and it is worth walking through each of them, because which one physics eventually walked through is the uncomfortable part. The first door is that one of the measurements is wrong, not fraudulent, not incompetent, simply affected by something nobody accounted for. In practice, this means an underestimated systematic uncertainty. Statistical error is the easy kind. It comes from having a finite number of events, and it shrinks predictably as you collect more. Systematic error is the hard kind. It comes from the apparatus, from the assumptions, from the corrections applied to raw data, and it does not shrink with more data because it is not random. If your ruler is slightly warped, measuring the table 1,000 more times will make you more confident in exactly the wrong answer. Systematic errors are where physics goes to embarrass itself, and every experimentalist knows it. The second door is that the theory connecting the measurement to the number is incomplete. Neither method sees a radius. Both see something else and convert. The scattering experiments see a pattern of deflections and fit it to a mathematical description called a form factor, then take the slope of that function as it approaches zero momentum transfer, which is a limit you cannot actually reach with a real beam, so the value has to be extrapolated inward from where the data stop. Different assumptions about the shape of that function give different slopes and therefore different radii from identical data. The spectroscopy experiments see a frequency and subtract from it an enormous stack of calculated quantum corrections, and what is left over at the bottom is the proton size term. If any correction in that stack is wrong, the leftover is wrong. The third door is the one nobody wanted. Both measurements are right, and the muon really does interact with the proton in some way the electron does not. The standard model asserts that the 3 charged leptons, the electron, the muon, and the tau, are identical in everything except mass. This is called lepton universality, and it is not a minor technical assumption. It is a load-bearing wall. If muons and electrons feel a different force from the same proton, then there is a new interaction in nature that couples to mass, and essentially, the entire structure of particle physics needs revisiting. There was a fourth possibility that lived in the doorway between the first two, and it received an enormous amount of attention. It is called two-photon exchange. When an electron scatters off a proton, the simplest description has a single particle of light passing between them, carrying the electromagnetic force. But quantum mechanics allows two to be exchanged instead, and while that process is rarer, it is not negligible at the precision involved here, and calculating it requires knowing something about what the proton does internally while the exchange is happening. That is the hard part, because the proton's internal behavior is exactly the thing nobody can compute cleanly. So there was a period in which a great many physicists hoped that the entire puzzle would turn out to be a mishandled correction of this kind, sitting quietly in the theory, affecting muons and electrons by different amounts because of their different masses. Careful work narrowed that possibility considerably. It did not, on its own, account for the size of the discrepancy. For most of the 2010s, all three doors stayed open. Then the evidence began to move, and it moved in a direction that is either reassuring or unsettling, depending on how closely you look. In 2019, a collaboration at the Thomas Jefferson National Accelerator Facility in Virginia published the result of an experiment called PRAD, and its design was a direct assault on the extrapolation problem. Because the radius comes from the behavior of the data as the deflection approaches zero, what you want is measurements at extremely small angles, as close to straight ahead as you can manage. Conventional experiments cannot get there, because a magnetic spectrometer physically cannot sit in the beamline. PRAD removed the magnet entirely and used a large calorimeter directly downstream, and it used a windowless hydrogen gas target, so the beam never passed through a container wall that would generate background it would then have to subtract. It reached angles far smaller than any previous electron scattering measurement, which shortened the extrapolation dramatically. The answer came back at 0.831 femtometers, with an uncertainty of 0.007 from statistics and 0.012 from systematics. That is 2.7 standard deviations below the average of every previous electron scattering result, and it sits comfortably alongside the mnemonic hydrogen value rather than the textbook one. At the same time, ordinary hydrogen spectroscopy was being repeated by several independent groups with modern equipment, and several of those measurements also came out low, consistent with the muonic value. The weight of evidence shifted. In the 2018 adjustment, the international committee responsible for the tables of fundamental constants stopped excluding the muonic hydrogen data, which it had previously set aside as an outlier. The recommended value dropped. The current co-data value from the 2022 adjustment is 0.84075 femtometers, with an uncertainty of 0.00064. That is, within its error, the muonic number. Randolph Pohl's team was right. So the puzzle is solved. That is how it gets reported, and in the practical sense it is fair enough. The number in the tables today is the small one. The disagreement has narrowed from 5 standard deviations to something manageable, and physics has moved on to other worries. Look more closely at the shape of that resolution, though, because there is something missing from it. Nobody ever isolated the mistake. There was no moment when a group announced that they had found the specific error in the older electron scattering work, published the correction, and watched the old value move to the new one for a stated reason. What happened instead is that the old measurements were gradually reassessed. Their uncertainties were judged to have been too optimistic. Newer measurements with better technique landed lower, and the internationally agreed value slid down to meet the muonic result over the course of about a decade. The number changed. The explanation for why decades of careful work by many independent groups had clustered around a value now considered wrong is, at best, a general one about the difficulty of extrapolation and the underestimation of systematics. That is not a scandal. It is how measurement science often works, and there is no villain anywhere in it. But it should adjust how you hear the phrase, "we know the size of the proton." What that phrase means is that the current best estimate, extracted through a chain of theoretical assumptions from data that does not directly show you a radius, agrees across several methods, at this level of precision, for now. And the third door has not actually been closed. The Muse experiment is still running at the Paul Scherrer Institute, and it exists to shut it properly. Its design is elegant. Rather than comparing an electron experiment done in one laboratory against a muon experiment done in another, with different apparatus and different systematics and different decades, Muse uses a mixed beam containing both electrons and muons of both charges and scatters them off the same hydrogen target through the same detectors at the same time. If electrons and muons see the same proton, the two datasets will agree, and lepton universality survives a direct test at sub% precision. If they do not, physics has a genuinely new problem. The measurements span 4 momentum transfer from 0.002 to 0.08 giga-electron-volts squared, and the collaboration has been taking and analyzing data through the 2020s. There is a reason that test is still considered worth running, and it is not stubbornness. The muon has been behaving oddly in other contexts too, most famously in the long-running measurements of its magnetic moment at Fermilab, where experiment and theory have circled each other for years without settling. When the same particle keeps appearing at the edge of anomalies, people keep checking. It is worth noticing what this whole episode cost, in a currency that does not appear in any paper. Roughly a decade of the attention of a substantial part of a research community went into a 4% disagreement about the size of one particle. Hundreds of papers, several new experiments, funded, built, and run. Careers spent. And the outcome was not a discovery. The outcome was that a number in a table was corrected, and the world went back to normal. That is what the overwhelming majority of physics actually looks like, and it is the part that never makes it into the public account, where results arrive cleanly and revolutions happen on schedule. Most of the work is people being extremely careful about a small thing for a very long time, and being rewarded with the news that they can now be slightly more careful. But the radius disagreement, for all the attention it received, was never the deepest problem with proton size. It was a disagreement about a number, and disagreements about numbers get resolved, one way or another. The deeper problem was sitting underneath it the whole time, and it does not resolve, because it is not a measurement problem at all. The question itself does not have a single answer, not because we lack the equipment, because of what the proton is. Part 6. It does not have an edge. Here is a question that sounds like nitpicking, and is not. When physicists quote the size of a proton, which size do they mean? There is more than one. The charge radius, the one we have been discussing, describes how the proton's electric charge is distributed. There is also a magnetic radius, describing the distribution of its magnetism, and it is a different number, measured by different means, and it does not have to match. There is a mass radius, describing how the energy and momentum inside the proton are spread out, which is probed through processes involving the strong force rather than electricity, and recent extractions from certain photoproduction data suggest it comes out smaller than the charge radius. There is a mechanical radius, associated with the distribution of internal pressure and shear, a quantity that has only become measurable in the last few years, and which describes something genuinely strange. The proton has an internal pressure profile, with the core under outward pressure of a scale that exceeds anything found in a neutron star, balanced by an inward pull further out. These are not competing estimates of one true value, they are different properties. The proton is not a ball with a definite size that several methods are trying to pin down. It is a distributed object whose electric charge, magnetism, mass, and internal stresses are each spread out in their own way, over their own characteristic distance, and asking which one is the real size is like asking whether the real size of a city is the built-up area, the commuter belt, or the boundary on the administrative map. All three are meaningful. None is the answer. The city does not have an edge. Neither does the proton. Let yourself approach one. You are shrinking, and the atom you are inside expands around you until the electron cloud is a haze somewhere far behind, and there is a single object ahead. At first, it behaves the way you expect. There is something there, and it is getting closer, and you brace for the moment you arrive at it. You keep going. The charge around you thickens, gradually, the way fog thickens on a road, and there is no point at which anything announces itself. You are waiting for a surface. There is no surface. There is more of it than there was a moment ago, and less than there will be. And this remains true continuously, without a step, without a wall, without a place where outside becomes inside. You pass what a physicist would call the radius, and nothing happens there, because that number was never a location. It was an average. It described how spread out this is, not where it stops. Somewhere near the middle, the density is at its greatest, and then, if you keep going, it begins to fall again, and you exit through the far side without ever having crossed anything. Behind you, the charge thins out and keeps thinning, mathematically forever, growing smaller than any measurement could ever detect, but never reaching zero. You have passed entirely through the most solid thing in the universe, and you never touched a boundary, because it does not have an edge. That is not a metaphor, and it is not a simplification for a general audience. It is the actual situation, and it is why the question, how big is a proton, cannot be answered with a single number without first agreeing on a convention. What physicists have done is choose a sensible convention, define it precisely, and measure it well. That is the right thing to do. But it means the number in the table is a description of a statistical property of a distribution, not a measurement of the extent of an object, and the two are not the same kind of fact. The internal pressure result is worth dwelling on because it is one of the more recent things anyone has learned about the proton, and it is not widely known. In 2018, physicists at the Jefferson Lab published the first experimental extraction of the pressure distribution inside a proton, using a process in which an electron knocks a high-energy photon out of it, and the way that happens encodes information about the internal mechanical structure. What emerged was a picture of a core under immense outward pressure, on the order of 10 to the 35 pascals near the center, which is greater than the pressure estimated for the interior of a neutron star, the densest object that exists short of a black hole. That outward pressure is contained by an inward-directed pressure in the outer region. The proton is not a placid little sphere. It is a standoff. Something inside it is pushing outward harder than anything else in nature, and something further out is holding it in, and the balance between the two is what you are made of. There is a further layer to this, which is that no experiment measures a radius at all. Every value ever published has been extracted, through a chain of theory, from something else that was actually observed, a pattern of deflected particles, a frequency of light. The radius is the output of a model applied to data. Change the model, and the number changes. This is true of a great deal of physics, and it is not a criticism. It is simply worth knowing, because the phrase we measured it carries an implication of directness that is almost never accurate at this scale. You might reasonably object that ordinary objects have this problem too, and you would be right. A table does not have a sharp edge either. Zoom in far enough, and there are atoms, and around those atoms are electron clouds with no boundary of their own, and the sensation of a hard surface is a phenomenon of electromagnetic repulsion, rather than a place where matter stops. The difference is that with a table, the fuzziness is so small relative to the object that no ordinary question is affected by it. You can define the edge of a table to within a fraction of a millimeter, and everyone will be satisfied. With the proton, the fuzziness is the object. There is nothing else. Take away the distribution, and there is no residual particle underneath it that the distribution was wrapped around. This is where the shaded circle from the classroom diagram does its real damage. It is not simply that the circle is drawn at the wrong size, or that its neighbours are misplaced. It is that the diagram promises there is a thing there with a definite outline, and there is not, and every subsequent question you ask inherits that assumption. How big is it? What is it made of? How much does it weigh? Each of those questions is phrased for an object with an inside and an outside and a fixed inventory of contents, and each of them will return a strange answer, or several incompatible answers, because it is being asked about something that does not have those features. Notice also what happened to the puzzle from the last part when viewed from here. Two groups measured the proton by different methods and got different numbers, and the physics community spent a decade determining which was correct. That was a real disagreement with a real resolution, but underneath it sat the fact that even in perfect agreement, with flawless apparatus and no systematic errors anywhere, the proton would still have several different radii, depending on which property you chose to spread out and measure. The 4% argument was happening on top of a much larger ambiguity that nobody was arguing about, because everybody in the field already knew about it and had agreed on a convention long ago. That is a pattern worth carrying forward, because it repeats. The public arguments in physics are usually about the last few percent. The genuinely disorienting facts are usually further down, settled, uncontroversial, and rarely mentioned, because within the field they stopped being surprising decades ago. It also means that a sentence you have heard many times is misleading in a specific way. People say that atoms are mostly empty space, and then, reaching for the dramatic version, that you are mostly empty space. The first part is fair. The second part imports the idea that the small dense bit at the center is the solid part, the real matter, the thing that is actually there, while everything around it is absence. That is the part that fails. The nucleus is not a tiny piece of genuine substance suspended in nothing. It is a region where fields are intense, with no more of a hard core at its center than the atom has at its own. You do not reach a floor by going smaller. You just find more activity, arranged more densely, all the way down to the limit of what anyone can currently probe. So the size question does not get answered. It dissolves. What you are left holding is a distribution rather than an object. And that raises the obvious next question, the one that sounds even simpler than the last one and turns out to be worse. If there is no outside, what exactly is on the inside? Part 7. What is actually inside? Let us step back for a moment and put the pieces together, because we have covered a lot of ground, and it is worth seeing the shape of it before we go further. We began with an object that is everywhere, in every atom of your body, in 3/4 of the ordinary matter in the universe, the most studied particle in the history of the subject. We watched it get invented in Manchester, out of flashes of light on a screen in a dark room, and settle into a comfortable role as one of the small handful of elementary things. We watched a man at Stanford discover that it was not elementary at all, but had structure and a measurable extent. We watched that extent get measured, agreed upon internationally, written into every textbook, and then contradicted by a team in Switzerland who assumed for years that the fault was theirs. We watched the number in the tables move to meet them without anyone ever producing the specific error. And then we found that underneath all of that argument sat a fact nobody was arguing about, which is that the proton has no boundary anywhere. So the question of its size has several legitimate answers depending on which property you decide to measure. Now we go inside, and this is where the description you were given at school stops being a simplification and starts being something closer to a fiction of convenience. You were told a proton is 3 quarks, 2 up, 1 down. Hold that in mind, and then hear the correct version. 3 is not a count of what is in there. It is a net figure. It is what remains after cancellation. In the same way that a company reporting 3 million in profit is not carrying 3 million in a box. The interior of a proton contains quarks and antiquarks in enormous and constantly changing numbers, appearing in pairs and vanishing again, along with gluons, the particles that carry the strong force between them. Subtract the antiquarks from the quarks of each type, and you are left with 2 up and 1 down. Those 3 are called valence quarks. Everything else is called the C, and the C is not a minor correction. At the energies of a modern collider, most of what is in there is C and gluons. Then it gets worse, in a way that is difficult to accept the first time you hear it. The amount of stuff inside a proton depends on how hard you look at it. That is not a statement about the limits of our instruments. It is a physical fact about the object. Probe a proton gently, with a low-energy particle, and you see something that behaves roughly like 3 quarks in a bag. Probe it violently, with a high-energy particle, and you resolve finer structure. And what you find is that each of those quarks is surrounded by its own swarm of gluons and pairs, and each of those gluons has its own. Increase the energy again, and more appears. The population you measure is a function of the resolution you brought with you. There is no final count that you would arrive at with a good enough microscope, because the constituents are not sitting there waiting to be counted. They are fluctuations of the fields, and how many of them are meaningfully present depends on the timescale over which you interrogate them. The mechanism behind this has a name, asymptotic freedom, and it earned 3 physicists the Nobel Prize in 2004. The strong force behaves in the opposite way to every force you have direct experience of. Gravity weakens with distance. Electricity weakens with distance. The strong force between quarks gets weaker the closer they are, and stronger as they are pulled apart. Inside a proton, at very short range, the quarks are almost free, rattling around with relatively little constraint. Try to remove one, and the force resisting you rises the further you go. Follow that to its conclusion. Take a quark and start pulling. The energy stored in the connection between it and its neighbors rises steadily, like stretching a rubber band that never thins. At some point, the energy in that stretched connection is greater than the energy required to make a new quark and antiquark from nothing, and so that is what happens. The connection snaps, and the break is filled instantly by a freshly created pair, and what you are holding is not a free quark, but a new particle, and what remains behind is another particle. Pull a quark out of a proton, and you do not get a quark. You get 2 objects, each containing quarks, and you are exactly where you started. This is, incidentally, what is happening in a particle collider, and it explains a detail that puzzles people the first time they see the pictures. When 2 protons meet at nearly the speed of light inside the Large Hadron Collider, the detectors do not record a spray of quarks. They record jets, narrow, tightly grouped showers of ordinary particles, dozens of them, all traveling in roughly the same direction. Each jet is the trace of a single quark or gluon that was knocked hard out of a proton, and then, in the act of leaving, converted the energy of its own departure into a cascade of new particles. You never see the thing that was struck, you see the debris of it refusing to be alone. Nobody has ever seen a free quark, not once, in any experiment, at any energy. Quantum chromodynamics says nobody ever will, and calls the principle confinement. Consider how peculiar that is, as a scientific situation. The entire modern description of matter is built on constituents which cannot, even in principle, be isolated and examined on their own. They are inferred from the behavior of the things they compose, and the theory that describes them predicts, as one of its central features, that they can never be extracted. The gluons that bind them have their own oddity, and it is the root of everything above. The particle that carries electromagnetism is light, and light has no electric charge, which is why 2 beams of light pass straight through each other. The particle that carries the strong force does carry the charge it responds to. Gluons pull on gluons. The force field interacts with itself, and that self-interaction is the reason the strong force does not thin out with distance the way every familiar force does, and the reason the interior of a proton is a churning, self-sustaining tangle rather than a few objects in a box. Which brings us to the result that ought to be more famous than it is. In August of 2022, the NMPDF collaboration published in Nature the outcome of a machine learning analysis of 4,618 measured cross-sections gathered from decades of collider data, looking for a signature that had been predicted more than 40 years earlier by Stanley Brodsky and his colleagues, and never confirmed. They found evidence for intrinsic charm. The charm quark is one of the heavy quarks. It has a mass of about 1,270 mega-electron-volts. The proton has a mass of about 938. Charm quarks had long been known to appear briefly inside protons during high-energy collisions, produced by the collision itself. Intrinsic charm is the claim that they are there anyway, not manufactured by the impact, but present as a persistent component of what the proton is, part of its structure over long timescales. Read that again slowly. The proton contains, as part of its ordinary composition, a particle that weighs more than the proton does. Quantum mechanics permits this. The constituents inside a bound system are not free particles with fixed, definite energies, and the relationship between energy and time in quantum theory allows configurations that simple arithmetic forbids, provided they do not persist in a way that could be caught out. That explanation is correct and complete, and it does very little to reduce the strangeness of the underlying fact. The history of that result is a small lesson in patience. Brodsky and his collaborators proposed intrinsic charm in the early 1980s. For 4 decades it sat in the literature as a plausible idea with inconclusive support, argued over periodically, neither established nor dismissed. Confirming it required not a new experiment, but a new way of looking at data that already existed, spread across many experiments and many years, with the signal buried in the interaction of hundreds of variables. The team used machine learning to disentangle the charm that was always there from the charm produced in the collision itself, which is a considerably harder distinction than it sounds. The person who first proposed the idea waited most of a career to see it supported. That is a fairly typical timescale, and it is one of the reasons the pace of physics is so poorly conveyed by the way discoveries are announced. So here is the honest answer to what is inside a proton. There is no list. There is no inventory you could write on a card. There is a probability distribution over configurations, whose composition depends on the energy at which you interrogate it, containing objects that can never be removed and examined, including at least one that is heavier than the container. When you are told you are made of atoms, and atoms are made of protons, and protons are made of quarks, every step in that sentence was doing something reasonable except the last one, where the word made of quietly stopped meaning anything like what it means when you say a wall is made of bricks. You are not built out of parts. You are a pattern that has been holding its shape for a very long time. And that pattern weighs something, which raises a question we have been circling since the first minute, and which is where this stops being an abstraction about particles and starts being about the number you would see if you stood on a scale. Part 8. Where the weight comes from. The proton has a mass of 938.272 mega-electron-volts in the units particle physicists use, where mass and energy are measured on the same scale because they are the same thing. Now, add up its parts. The up quark has a mass of roughly 2.2 mega-electron-volts. The down quark is heavier, at roughly 4.7. A proton is 2 ups and a down. 2.2 plus 2.2 plus 4.7. That comes to about 9.1. 9.1 against 938. The quarks account for slightly under 1% of the mass of the proton. 99% of the weight of the thing you are made of is not the weight of anything inside it. This is the single most misrepresented fact in popular physics, and the misrepresentation has a specific source. When the Higgs boson was discovered in 2012, it was explained to the public over and over as the particle that gives everything else mass. That sentence is true in a narrow technical sense, and profoundly misleading in every practical one. The Higgs field does give mass to the fundamental particles, to the quarks, to the electron, to the W and Z bosons. But the mass it gives the quarks inside you is that 9.1 out of 938. Roughly 1%. If the Higgs field switched off tomorrow and quarks became massless, the proton would still weigh about 99% of what it weighs now. So where does the rest come from? It comes from energy. Specifically, from three things. Around a third of it is the kinetic energy of the quarks, which are moving at speeds close to that of light inside a space about a femtometer across, and are heavy in the sense that anything moving that fast carries enormous energy. Rather more than a third is the energy of the gluon field, the tangle of self-interacting force that binds them and that we walked through in the last part. And around a quarter comes from something with no classical counterpart at all, called the trace anomaly, which arises because the theory of the strong force does not respect a scaling symmetry that the equations naively appear to possess. The symmetry is broken by quantum effects, and the breaking has an energy cost, and that cost is part of what you weigh. A lattice calculation published in 2018 put approximate numbers on the split, about 32% from quark kinetic energy, about 37% from gluon kinetic energy, about 23% from that quantum anomaly, and the remainder from the quark masses themselves. None of this is speculation. In 2008, a team led by Stefan Durr published in Science a calculation of the masses of the light hadrons, including the proton, derived from the theory of the strong force alone, with no experimental input beyond a handful of parameters. They reproduced the proton mass to within a few percent. The theory works. It gets the right answer. Given quantum chromodynamics and enough computing time, the number 938 comes out the other end. But notice what kind of achievement that is. The calculation is a numerical simulation. It works by dividing space-time into a grid of discrete points, placing the fields on that grid, and evaluating an astronomically large integral by statistical sampling, consuming tens of millions of processor hours on some of the largest machines available. It is not an equation you can write on a page and look at. There is no derivation a person can follow from beginning to end and come away saying, that is why the proton weighs what it does. We have a machine that produces the correct number and a general sense of which physical effects contribute how much. That is genuine knowledge, and it is a different thing from understanding. Now stand on a bathroom scale. The number comes up, the way it always does. Trace where it comes from. Most of your body is water, and most of the weight of water is in the oxygen and hydrogen nuclei, so almost all of that number is nuclei. Go down into one. It is protons and neutrons, packed close. Go into a single proton. There are the quarks, and if you weighed only them and did the same for every proton and neutron in your body, the scale would read about 1% of what it actually reads. A person of 80 kilograms would come out at under a kilogram. Everything else, the 79 kilograms that make you a body rather than a rumor, is the energy of quarks moving and gluons pulling, and a quantum anomaly in a field theory. It is not substance, it is activity. If that activity stopped, there would be nothing left over that had been carrying the weight all along, because there was never anything else there. Sit with that for a moment, because it is the most personal fact in this entire story, and it deserves more than a sentence. You have an intuition, built from a lifetime of picking things up, that weight is a measure of how much stuff is present. Heavy means more material. That intuition is correct for boxes and bricks and bags of sand, and it is correct because those things are made of atoms and you are comparing counts of atoms. Go one level below that, and it fails completely. Your mass is not a measure of how much matter you contain. It is very nearly a measure of how much is happening inside you. And it has been happening without pause, in every proton in your body, for the entire time those protons have existed, which for the overwhelming majority of them is, since the first few minutes after the beginning of the universe. Not one of them has ever rested. The activity that constitutes your weight has been running continuously for 13.8 billion years. The word for this is not illusion. That is the wrong conclusion, and it is the one the internet reaches for. Your weight is entirely real. It will break a floor. The point is not that matter is fake, but that matter is a process, and that the noun you have been using your whole life describes a verb. There are a few footnotes worth having, because they sharpen it rather than softening it. Electrons are different. An electron genuinely does get essentially all of its mass from the Higgs field, in the way the popular explanation describes. But electrons contribute only about 1/20th of 1% of the mass of an atom. The part of you that behaves the way the public story says is a rounding error on a rounding error. If the quark masses were set to zero entirely, the proton would lose about 1% of its mass and carry on. But the world would not carry on, because those small masses matter for something other than weight. The neutron is heavier than the proton by about 1.3 mega-electron-volts, and that difference is what makes hydrogen stable, which is why there are stars that burn for billions of years, and why there is water, and chemistry, and you. That gap depends on the difference between the up and down quark masses, together with an electromagnetic contribution that pushes the other way. Change those small numbers by a modest amount, and the ordering flips. Protons decay into neutrons, hydrogen becomes unstable, and the universe contains no lasting atoms at all. The 1% that comes from the Higgs is almost irrelevant to your weight, and almost entirely responsible for your existence. And the energy that constitutes your weight is not locked away where it can never be touched. A small fraction of it is accessible, and human beings have already learned to release it. When 4 hydrogen nuclei fuse into helium in the core of a star, the resulting nucleus weighs slightly less than the 4 that went in, by about 7/10 of 1%, and that missing mass leaves as energy. 7/10 of 1% is what lights every star in the sky, what has kept the sun burning for 4.5 billion years, and what powered the weapons that ended a war. Nuclear fission releases a smaller fraction still, around 1/10 of 1%. Everything humanity has ever done with nuclear energy has involved skimming a sliver off the top of the binding energy inside nuclei, and the whole reserve underneath, the 99%, has never been touched by anyone, and probably never will be. So the mass problem is not a crisis in the way the radius problem was. Nobody is measuring conflicting values. The theory reproduces the number. It is a comprehension problem. We can compute what you weigh, and we cannot explain it to you. And the honest summary of where 99% of your body mass comes from is that it comes from the interior of a particle doing something no human being can picture. That is 3 of the 4. Size, contents, mass. Each one stranger than the last, and each one at least under control, in the sense that somebody somewhere knows how to calculate it. The 4th one is not under control. It has been open since 1987. It has consumed 4 decades and several accelerators, and it concerns the simplest property the proton has. Part 9. The spin nobody can find. The proton has spin 1/2. It is one of the simplest statements you can make about it, and it is a statement nobody can currently account for. Start with what spin is, because the word is one of the worst in physics, and it has been misleading people for a century. Spin is an intrinsic angular momentum carried by a particle. It is measured in the same units as the angular momentum of a spinning wheel. It adds and subtracts the way ordinary rotation does, and it determines how the particle behaves in a magnetic field. And nothing is turning. A proton is not a tiny ball rotating on an axis. If you tried to model it that way and calculated how fast the surface would have to move to generate the observed angular momentum, you would find that parts of it would need to be traveling faster than light. It is a property the particle simply has, in the way it has charge, and the name is a historical accident that everyone is now stuck with. For a while, the arithmetic looked easy. Each quark carries spin 1/2. Line up two of them opposed so they cancel, leave the third pointing, and the total comes to 1/2, which is what is observed. 3 quarks, 1 spin, done. That was the picture through the 1970s and into the 80s, and there was no obvious reason to check it. There had been a warning much earlier that nobody quite recognized. In 1933, Otto Stern measured the magnetic moment of the proton, which is how strongly it responds to a magnetic field. Theory at the time, from Dirac's equation, made a firm prediction for what a simple, structureless particle of that charge and mass should give. Stern measured about 2.79 times that value. It was flatly wrong, by a large margin, and it was one of the first indications that the proton was not the simple object it appeared to be. Stern received the Nobel Prize for it. The measurement sat there for decades as a curiosity, and its real meaning, that there was internal structure generating extra magnetism, only became clear later. In 1987 and 1988, the European muon collaboration at CERN went looking for the spin directly. The experiment is conceptually clean. Take muons, polarize them so their spins all point the same way, fire them at a target of protons whose spins have also been aligned, and measure how the scattering depends on whether the two are aligned or opposed. From that dependence, you can extract how much of the proton's spin the quark spins are actually carrying. The expected answer was most of it, perhaps 60%, allowing for relativistic effects that would reduce the naive figure somewhat. The measured answer was consistent with almost none. The published range was around 4 to 24%, and within its uncertainty, it was compatible with 0. The quarks, which everyone had assumed supplied the proton's spin, might have been supplying essentially none of it. The phrase spin crisis appeared in the literature within months, and it has never really left. The result was checked and rechecked, and it held. Something was carrying the angular momentum of the proton, and it was not the thing everyone had assumed. 40 years of work have improved the picture without closing it. Better measurements, particularly in the region where individual quarks carry only a small fraction of the proton's momentum, have pushed the quark spin contribution up from near 0 to around 30%. So the original result was too extreme. Quarks do carry some of it. They carry roughly a third. The other 2/3 has to come from somewhere, and there are only 2 candidates. The first is the spin of the gluons. Gluons carry spin 1, and if they are polarized on average, they contribute. Measuring that required colliding protons whose spins were aligned, which is what the relativistic heavy ion collider at Brookhaven National Laboratory was uniquely able to do, and the Star and Phoenix experiments established over many years that the gluon contribution is positive and significant. It is not, however, enough to close the gap on its own. There was a period, in the years after the crisis broke, when one proposed solution had the field's attention for entirely mathematical reasons. Because of a subtle quantum effect known as an anomaly, the gluon contribution enters the accounting in a way that is not straightforward, and it was pointed out that if the gluons in a polarized proton carried something like 4 full units of spin, the books would balance and the crisis would evaporate. It was an elegant escape. The difficulty was that nobody could produce any physical reason for gluons to be polarized to that degree, and when the measurements eventually came in from Brookhaven, they were nothing like large enough. The proposal is a good illustration of how these episodes actually proceed. A number goes missing, someone finds a place it could be hiding, everyone examines that place carefully for a decade, and it is not there. The second candidate is orbital angular momentum, quarks and gluons moving around inside the proton, carrying angular momentum by circulating rather than by intrinsic spin. Almost everyone expects this to be a substantial part of the answer. Measuring it is genuinely hard, and the difficulty is not only experimental. There is a long-standing technical dispute about how to define the orbital angular momentum of a quark inside a proton in a way that is consistent with the gauge symmetry of the theory. Different definitions carve the total up differently, and they are not simply matters of taste, because they correspond to different observable quantities. 4 decades in, physicists are still arguing about the correct way to write down the question. That should sound familiar. It is the same shape as the radius problem, one level deeper. There, the trouble was that the proton has no boundary, so size has several legitimate meanings, and you must state which one you want. Here, the trouble is that the proton's angular momentum cannot be split cleanly into pieces belonging to identifiable constituents, so the accounting has several legitimate forms. It does not have an edge, and it turns out that neither do the questions. Each one, pressed hard enough, stops having a single answer and becomes a family of related answers that depend on how you set it up. There is a detail here that makes the whole thing land differently. Magnetic resonance imaging works by manipulating the spin of the protons in the water in your body. A strong magnetic field aligns them, a radio pulse tips them, and the signal they give off as they settle back is assembled into an image of your interior. Millions of people are scanned this way every year. Every one of those scans depends on a property of the proton, whose origin has been an open problem in physics since 1987. The technology works perfectly. It does not require anyone to understand where the spin comes from, only that it is there and behaves predictably. That gap between the engineering and the explanation is wider in physics than most people imagine. The scale of the effort now going into closing it is the best evidence that it is genuinely open. In February of 2026, the relativistic heavy ion collider completed its 25th and final run, after a quarter of a century of operation. One of its 2 rings of superconducting magnets is being dismantled. In its place, at the same site, the electron-ion collider is being built, with conventional construction having begun in June of 2026 and operations expected in the first half of the 2030s. It will collide polarized electrons at energies from 5 to 18 giga-electron-volts, with polarized protons at 41 to 275, and its stated purpose is to produce 3-dimensional images of the interior of the proton, where the quarks and gluons sit, how they move, how their momentum and angular momentum are distributed in space. There is something quietly moving about that transition, if you have followed the story this far. A machine that ran for 25 years, that discovered a state of matter last seen microseconds after the beginning of the universe, that spent much of its life colliding spinning protons in order to find out what makes them spin, is now being taken apart by hand so that its successor can be threaded through the same tunnel. Engineers are removing cryogenic plant and radio frequency cavities from one ring while the other is kept alive. The people installing the new components will spend the better part of a decade on it, and the answers, if they come, will arrive in the 2030s, roughly 50 years after the European muon collaboration first noticed that the spin was missing. It is a multi-billion-dollar machine, decades in planning, and it is being built because we cannot answer the questions in this video. Not because the answers are almost within reach and need confirming, because they are open. 3 problems have now been laid out, and the 4th is different from all of them, because the first 3 are about description. They ask what the proton is. The fourth asks how long it lasts, and it is the only one where the answer changes what happens to everything else in the universe. It is also the one where everybody, for a very long time, assumed there was nothing to worry about. Part 10. The one thing everyone assumed. Everything in particle physics falls apart. That is close to a rule. Hundreds of particles have been catalogued over the last century, and almost all of them exist for a fraction of a second before decaying into something lighter. Most of them last so briefly that they are not observed directly at all, only inferred from the debris. Even the ones that look permanent mostly are not. A neutron, sitting inside an atomic nucleus, is stable for as long as the nucleus holds together, but take it out and set it on its own, and it lasts about 15 minutes before turning into a proton, an electron, and an antineutrino. 15 minutes. The neutron is the proton's near twin, differing by 1 quark and about 1 part in 700 in mass, and left to itself it does not survive the length of a walk to the shops. The proton does not do this. Out of every particle built from quarks that anyone has ever catalogued, it is the only one that appears not to decay at all. Not slowly, not eventually. As far as any measurement has ever been able to establish, it simply persists. Ask why, and the standard model gives an answer that looks solid until you inspect it. Protons are stable because of the conservation of baryon number. Baryon number is a bookkeeping quantity. Quarks carry 1/3 of a unit each, so a proton has 1, and the rule says the total across any interaction cannot change. Since the proton is the lightest particle carrying baryon number, there is nothing lighter for it to turn into without violating the rule. It has nowhere to go. Now inspect the rule. Where does it come from? In physics, conservation laws normally come from symmetries, and those symmetries are usually built into the structure of the theory for a reason. Energy conservation comes from the fact that the laws of physics do not change over time. Momentum conservation comes from the fact that they do not change from place to place. These are deep statements about the world. Baryon number conservation is not like that. Nobody put it in. It is what physicists call an accidental symmetry. It holds in the standard model, because once you have written down all the terms that the theory's structure permits, it happens that none of them changes baryon number. It is a consequence of the particular list of ingredients, not of any underlying principle. Nothing forbids baryon number violation in the way that something genuinely forbids a perpetual motion machine. It just does not occur in the specific model we happen to have. That distinction is the difference between a law and a coincidence, and it matters enormously, because as soon as you extend the theory, the coincidence tends to break. Extending the theory is exactly what physicists spent the 1970s trying to do. The standard model describes 3 forces with 3 separate mathematical structures bolted together. It works extraordinarily well, and it is not beautiful, and the strength of each of those 3 forces changes with energy in a way that can be calculated. When you extrapolate them upward, they converge. Not perfectly, but suggestively, at an energy around 10 to the 16th giga-electron volts. That looks like a message. It looks as though the 3 forces are aspects of one force, which splits into 3 at low energy, the way a beam of white light splits into colors. Theories built on that idea are called grand unified theories, and the first of them was written down by Howard Georgi and Sheldon Glashow in 1974. It was elegant and economical. It placed quarks and leptons into the same mathematical family, which is an appealing thing to do, because it would explain the coincidence we noticed earlier, that the charge of the proton exactly balances the charge of the electron. If quarks and electrons are members of one family, related by a symmetry, their charges must be related, and the mystery dissolves. But putting quarks and leptons in the same family has a consequence you cannot avoid. If they belong to one structure, there must be interactions that turn one into the other. and a quark turning into a lepton changes baryon number. So the proton, which had nowhere to go, suddenly has somewhere to go. It can decay. The most commonly predicted route is that a proton decays into a positron, the antimatter counterpart of the electron, and a neutral pion, which itself immediately decays into two photons. From the outside, you would see a flash of light and a positron, and the baryon that had existed since the beginning of the universe would be gone. The theory made a number. Georgi and Glashow's original model predicted a proton lifetime of the order of 10 to the 31 years. That figure requires a moment. The universe is about 14 billion years old, which is 1.4 times 10 to the 10th. A lifetime of 10 to the 31 years is about 100 billion times the age of the universe. On the face of it, this is the least testable prediction anyone has ever made. Except it is not, and the reason is the thing that makes this whole story possible. A lifetime of 10 to the 31 years does not mean every proton lasts exactly that long and then stops. It means each proton has a certain small probability of decaying in any given year. Radioactive decay works this way, and so does this. So you do not have to wait. You need only assemble a very large number of protons and watch them all at once. If you gather 10 to the 32 protons and watch them for a year, and the lifetime really is 10 to the 31 years, you should see roughly 10 decays. 10 to the 32 protons is not an unreasonable quantity. It is a few thousand tons of ordinary matter. Water will do, and water has the advantage of being cheap, transparent, and easy to purify. So the prediction was testable after all, and in the late 1970s and early 80s, several groups set out to test it. The expectation at the time was genuine optimism. Grand unification was widely believed. The number was within reach. People expected to find proton decay within a few years, collect their prizes, and open a window onto physics at energies no accelerator will ever approach. Some of them said so publicly. It is worth being clear about what was at stake in that expectation, because it is easy to treat this as an abstract question about a subatomic particle. If protons decay, then everything made of them has a finite life. Not a long life, a finite one. Every atom in every star, every planet, every body, in every galaxy has a small chance each year of coming apart. And given enough time, all of it does. Matter would not be a permanent feature of the universe, but a phase, and the far future would consist of the debris left over after the last proton went. There is a further reason the timing of that optimism mattered. The energy at which the three forces appear to converge, around 10 to the 16th giga-electron-volts, is not an energy any machine will ever reach. The Large Hadron Collider operates around 10 to the 4th. To probe unification directly, you would need an accelerator larger than the solar system, and that is not a funding problem, it is a physical one. So proton decay was never simply one more experiment. It was the only practical way anyone could see of getting information about physics at that energy scale, because the proton itself, sitting in a tank of water, is subject to those interactions whether or not we can build a machine to reproduce them. A single decay would have been a message from an energy scale that is otherwise permanently out of reach. Different versions of the theory predicted different routes and different timescales. Supersymmetric grand unified theories, which became popular through the 80s and 90s, often favored a decay into a kaon and an antineutrino rather than a positron and a pion, and generally pushed the lifetime longer. The details varied. The central claim did not. Baryon number is not sacred, and the proton is living on borrowed time. The energy involved in a single decay is worth stating because it explains why this is detectable at all. A proton carries 938 mega-electron-volts of rest energy, and when it decays, essentially all of that is converted into the motion of the products. On the scale of a subatomic event, that is a substantial amount. The positron, and the photons come out fast enough to leave an unmistakable signature in a suitable detector, which is why a single event, anywhere in a tank of thousands of tons, is in principle enough. You are not looking for a subtle statistical excess. You are looking for one clear flash, once, and then you have overturned a law. There was already a crude limit before anyone built anything, and it came from the human body. If protons decayed rapidly enough, the energy released inside a person would be measurable as radiation. You are made of about 10 to the 28 protons. If the lifetime were as short as 10 to the 18 years, you would be detectably radioactive from the inside, and you are not. Simply not glowing was enough to establish a flaw. To go further than that, you need to watch a great deal of matter for a very long time, in a place where nothing else can interfere. Which is why, in the early 1980s, physicists went underground. Part 11. 50,000 tons of water in the dark. The first serious attempts began in the early 1980s. One was in a salt mine beneath Lake Erie in Ohio, run by a collaboration from Irvine, Michigan, and Brookhaven. Another was in a zinc mine in the Japanese Alps, near a place called Kamioka, and it was named after the mine. Both were tanks of purified water, thousands of tons of it, buried under as much rock as could be arranged. The rock is not incidental. At the surface, cosmic rays from space strike the atmosphere continuously and shower the ground with particles. Any detector sensitive enough to register a single proton decay would be overwhelmed by that background within a fraction of a second. Kilometers of stone above your head filter it out, absorbing almost everything and leaving only the most penetrating particles behind. Every experiment of this kind is buried in a mine or under a mountain for that reason alone. The successor to the original Japanese detector is the one that has done most of the watching. Super Kamiokande sits about 1 kilometer below the summit of Mount Ikeno. It is a cylindrical stainless steel tank, roughly 40 meters across and 40 meters tall, holding 50,000 tons of ultra-pure water. Lining its walls are more than 11,000 photomultiplier tubes, each about 50 centimeters in diameter, each capable of registering a single particle of light. It began operating in 1996, and it has been running, with breaks for maintenance and repair, ever since. The physics it exploits is straightforward and rather beautiful. Nothing can travel faster than light in a vacuum, but light itself travels more slowly through water, and a charged particle can exceed that reduced speed. When it does, it produces an optical shock wave, a cone of blue light trailing behind it, in the same way that an aircraft exceeding the speed of sound trails a cone of pressure. It is called Cherenkov radiation. A proton decaying into a positron and a pion would produce fast charged particles, and those particles would produce cones of blue light, and those cones would strike the walls in rings, and the pattern and timing of which tubes light up and when would reconstruct the event. Picture being in there. During a maintenance period, the tank is partly drained, and physicists cross the surface of the remaining water in an inflatable boat, moving slowly between walls of glass. Above and below, and on every side, are the photomultipliers, 11,000 of them, each the size of a beach ball, each polished, each pointing inward. The water is so pure that light passes through tens of meters of it before being absorbed. Purer than anything you would ever encounter. So clear that judging distance across the tank is difficult. When the tank is sealed and full and running, that space is in total darkness, and it stays in total darkness. And 11,000 glass eyes watch it continuously, every second, for a flash. Somewhere in that volume are protons that formed in the first few minutes after the beginning of the universe, and have been intact ever since. The detector has been watching them for 30 years. Nothing has happened. That is the result. Not a small signal, not an ambiguous excess, not something requiring careful statistical argument. In 3 decades of continuous observation of an enormous quantity of matter, no proton has ever been seen to decay. The current limit, at 90% confidence, is that the lifetime for the channel into a positron and a neutral pion exceeds 2.4 times 10 to the 34 years. Set that against the age of the universe, which is about 1.4 times 10 to the 10th years. The measured floor under the proton's lifetime is more than 10 to the 24th times the current age of the universe. A trillion times. If you had started watching a single proton at the beginning of time and waited until tonight, you would not have observed a millionth of a billionth of a percent of the span over which we now know it must survive. Getting to a number like that requires being certain about what you did not see, which is harder than being certain about what you did. The water has to be purified continuously, because natural water contains trace radioactive isotopes that would produce their own flashes. Neutrinos from the atmosphere pass through the detector constantly and occasionally interact, producing events that can imitate the signature being searched for, and each one has to be identified and set aside. The ring patterns from different particles differ subtly. An electron, or positron, produces a fuzzy, scattered ring because it showers as it travels, while a muon produces a sharp one. Distinguishing them, event by event, over decades, is most of the work. A claim that nothing happened is only as strong as the argument that you would have recognized it if it had. That number killed a theory. The original Georgy Glashow model predicted around 10 to the 31 years. The experiments passed that in the 1980s and kept going. The minimal version of the first grand unified theory, the elegant one, the one that explained why the proton's charge matches the electron's, was ruled out by an absence. Nothing happened, and that was the result. It is worth pausing on how unusual that is as a scientific outcome. Most theories die when an experiment finds something they said would not be there. This one died because an experiment did not find something for long enough, with enough matter under observation, that the silence became conclusive. Several generations of physicists have now built their careers around watching for an event that has never occurred, and the accumulated weight of that non-occurrence has excluded large regions of theoretical possibility, pushing the energy scale of unification above roughly 10 to the 16th giga-electron volts. The nothing is the data. The tank has not been entirely quiet, and one incident is worth telling. In 2001, during a refill after maintenance, a single photomultiplier tube at the bottom of the detector imploded under the water pressure. The shock wave from that implosion struck its neighbors, which imploded, and the wave spread outward through the array. In a few seconds, around 7,000 of the 11,000 tubes were destroyed. The detector was rebuilt with protective casings around every tube, and it went back to watching. That is the character of the Enterprise. An accident that would have ended most projects was treated as an interruption in a program measured in decades. Consider also what a career looks like inside a program like this. A physicist who joined the original Kamiokande collaboration as a graduate student in the early 1980s, expecting to see proton decay within a few years and to be part of the most important result of the century, would now be near the end of a working life. They would have spent it maintaining, calibrating, analyzing, rejecting backgrounds, writing papers whose central finding is a limit. Every one of those papers says, in effect, still nothing, and here is how much more confident we are about the nothing. There is a particular kind of patience in that, sustained across a whole community for 4 decades, with no reward at the end, except a number that keeps getting larger. There is one more thing that Tank has done, and it reframes everything. In 1998, Super Kamiokande announced that neutrinos, the near-massless particles that stream through the Earth in unimaginable numbers, change type as they travel. That oscillation is only possible if neutrinos have mass, and the standard model had said they did not. It was a genuine discovery, and it earned Takaaki Kajita a share of the Nobel Prize in 2015. So the same detector, in the same water, under the same mountain, failed completely at the thing it was built to do, and succeeded at something nobody had commissioned it for. The people watching for a proton to break found instead that a different particle was not what everyone thought it was. That is not a consolation prize. It is a fair description of how discovery usually works, and it is worth remembering the next time someone describes a null result as a wasted effort. But the proton question was left exactly where it started, only sharper. We have not established that the proton is stable. Let that land properly, because it is the point the entire second half of this has been building toward. 30 years of watching 50,000 tons of water in the dark has not demonstrated that protons last forever. It cannot. No experiment ever could. What it has established is a flaw. Whatever the proton's lifetime is, it is longer than 2.4 times 10 to the 34 years. The true value could be 100 times that, or 1,000,000,000 times, or genuinely infinite, and the measurement cannot distinguish between those cases. It can only keep pushing the flaw upward, which means the question in the title of tonight's story has never been answered, not because nobody has tried, because of the shape of the question itself. So, why won't it die? There are two possible answers, and this is the part where they stop being technical. Part 12. Why it will not die, and what that costs. Here is the answer, plainly, as promised. Nobody knows whether the proton dies. We have never established that it is stable. What we have established is a flaw. It lives longer than 2.4 times 10 to the 34 years. That is a statement about the limits of our patience and our tanks of water, not a statement about the proton. The truth lies on one of two sides of that flaw, and this is the part that makes the question worth 2 hours of your evening, because both sides are unwelcome, and the more comfortable sounding one is arguably the worse. Take the first branch. Suppose protons do decay, somewhere beyond our current reach, perhaps at 10 to the 36 years, or 10 to the 40, and we simply have not watched long enough or gathered enough matter. Then everything made of matter has an expiry date, not a metaphorical one. Every atom in your body, in this planet, in every star, in every galaxy, has a small probability each year of coming apart into lighter things. Over ordinary timescales, it is invisible. Over the timescales the universe actually has available, it is total. The stars burn out, the last of them fading somewhere around 100 trillion years from now. The remnants cool. And then, across a span so long that the entire stellar era counts as an opening flicker, the remnants themselves evaporate from the inside, atom by atom, as protons decay into positrons and light. What is left is a thin, cold fog of radiation and stray particles, expanding, with nothing in it that could ever be assembled into anything again. Matter turns out to have been a phase, and a brief one, and we happen to be alive during it. In that future, the last structures to survive are the ones that were never made of protons in the first place. Black holes have no atoms in them, nothing to decay, and they persist long after the ordinary matter around them has evaporated away. They leak slowly, radiating themselves out of existence over spans that dwarf everything preceding, and the largest of them are still there when nothing else is. So the final era of that universe, if this branch is the right one, belongs to objects made of collapsed space-time rather than to anything built from particles. Everything that could ever be assembled into a star, a planet, a molecule, or a person would have already come apart, and the last things burning would be the places where matter had stopped being matter altogether. Now take the second branch. Suppose the proton is genuinely stable. Suppose baryon number is exactly conserved, protons never decay, and matter is permanent. You would think that is the reassuring answer. It is not, and the reason takes us back to the beginning of the universe. In 1967, the Soviet physicist Andrei Sakharov set out 3 conditions that must be satisfied for a universe to end up containing more matter than antimatter. The first and most important is that baryon number must be violated. There must be some process, at some point, capable of changing the number of protons in the universe. The reasoning is unavoidable. If the early universe began with equal amounts of matter and antimatter, or with nothing but energy, and if the total number of baryons can never change, then the total must remain 0 forever. Every proton would be balanced by an antiproton, and they would find each other and annihilate, and the universe would contain radiation and nothing else. No stars, no planets, no chemistry, no listener. You exist, therefore the number of protons in the universe changed at least once. Therefore, baryon number is not exactly conserved. That is the trap, and it is worth stating as directly as possible. The property that would doom all matter is the same property that explains why there is any matter to doom. If protons can never decay, then nothing could ever have created the excess of matter that everything is made of, and the existence of a universe containing anything at all becomes harder to explain rather than easier. Sakharov's other 2 conditions are worth naming because together they describe a very particular kind of accident. The second is that the laws of physics must treat matter and antimatter slightly differently, which they do, in a small effect, first seen in 1964 and measured many times since. The third is that the universe must have departed from thermal equilibrium at the relevant moment, because in perfect equilibrium, any process that creates an excess runs equally in reverse and destroys it. All 3 have to hold at once. The universe had to break its own bookkeeping, prefer one side over the other by a tiny margin, and do so while cooling too fast to undo it. The surviving excess amounts to roughly 1 extra particle of matter for every billion pairs that annihilated. Everything that exists is the remainder after that cancellation. There is an escape route, and it is currently the favored one. It is called leptogenesis. The idea is that the original asymmetry was generated among neutrinos rather than among protons, and was later converted into an asymmetry in ordinary matter by processes in the very early universe that violate baryon number in a specific combined way, without permitting proton decay at any rate we could ever detect. If that is what happened, the proton could be stable for all practical purposes, and the universe could still be full of matter. It is a serious proposal, supported by the discovery that neutrinos have mass, which came, appropriately enough, from the same tank of water that failed to find proton decay. But notice that even the escape route requires baryon number to have been violated at some point. The rule you were given, the one that keeps the proton alive, is not a law of nature. It is a feature of the theory we happen to have, in the energy range we happen to inhabit, and the universe demonstrably broke it at least once, early, when the conditions were different. So the honest position is this: we do not know if the proton decays. We know it has not decayed in front of us, in the largest quantities we can assemble, over the longest period we have been watching. Nothing happened, and that was the result. And that result is simultaneously the most precise measurement in this entire story, and the least conclusive. It rules out theories. It does not answer the question. The watching continues. Hyper Kamiokande is under construction in Japan, a tank several times the size of its predecessor, designed to extend the reach by roughly a factor of 10, out toward 10 to the 35 years. If protons decay anywhere near the range that many grand unified theories still favor, it has a chance of seeing it. If it sees nothing, the floor rises again, more theories die by absence, and the question passes to whoever builds the next one. And there are stranger possibilities beyond the ordinary ones. Some models suggest that even if the known interactions preserve baryon number perfectly, Gravity may not, and protons could decay through fleeting quantum black holes at timescales that make 10 to the 35 years look immediate. Others point out that even a perfectly stable proton does not guarantee stable matter, because over long enough spans, everything tunnels toward the most tightly bound configuration, and cold matter would slowly transmute into iron over something like 10 to the 1500 years. There is no version of the future in which things simply stay as they are. There are only different accounts of how long the arrangement lasts. Which brings us back to where we started, and to a phrase that should sound different now than it did 2 hours ago. The proton is the most familiar object in the universe. It is in every atom of you, and in 3/4 of the ordinary matter that exists, and it is the most studied particle in the history of science. And after all of that, here is what can be said about it plainly. We cannot state its size without first choosing which of several incompatible definitions of size we mean, because it does not have an edge. We cannot list what is inside it, because the contents depend on how hard we look, and include a particle heavier than the whole. We can calculate its mass, and we cannot explain it, and 99% of your body weight is the answer to a question no human being can picture. We have been unable to account for its spin since 1987, and a machine is being built right now, at a cost of billions, largely to find out where it is. And we cannot say whether it lasts forever, only that it lasts longer than we have been able to watch. 5 properties. Not one of them can be stated in a plain sentence. That is the thing worth carrying away from tonight, more than any single number. We tend to assume that studying something makes it clearer. The proton is the strongest counterexample in physics. A century of increasingly precise attention has produced a description that is more accurate and less comprehensible with every decade, and every question that seemed simple has turned out, on inspection, to have no single answer. The more scientists study the proton, the less sense it makes. There are protons in you tonight that formed in the first 3 minutes of the universe, before there were atoms, before there were stars, before there was anything to be part of. They have been intact through every event since. They will be there in the morning. Whether they will be there at the end of everything, nobody can tell you, and the people best placed to know have spent 40 years in the dark, under a mountain, watching and waiting for the one flash that would settle it.